This lecture is part of an online course of multivariable calculus, and I'm going to talk about change of variables for double integrals. So let me start. Assume that we want to compute the double integral of f dA over the region R using change of variables like this. So for example, u is 2x minus y, and then I'm going to take v as x minus 3y. Okay. Instead of any x that we see in the function f, and instead of any y, we can replace them with u and v. After we write x in terms of u and v and y in terms of u and v, and then we're going to change the region R with respect to u and v as well. The question is this: what is the relation between dx dy, basically dA, how can I change dA, and du dv? So dx dy is just basically the element, the area element in xy plane, and du dv is basically the area element in uv plane after we change the variables. So now let's consider a small rectangle in xy plane. Let me graph the rectangle. This is x-axis, this is y-axis, and I have a small rectangle in here. One side of the rectangle is delta x, the other side is delta y. So the area of this rectangle is delta A, which is delta x times delta y. Okay, in UV plane, I'm gonna move this one a little bit so that I have a space for UV plane. U-axis, V-axis. So this rectangle in UV plane becomes a parallelogram like this. Okay. The area of this one is delta A. I'm going to call the area of the parallelogram with delta A prime. And after the transformation, this rectangle becomes the parallelogram. And now I'm going to see exactly what do I get. What is the parallelogram that I get if I have this transformation. So since we have a linear change of variables in here, it doesn't matter that which rectangle you take to figure out the relation between delta A and delta A prime. So I'm gonna just pick something very simple. So let's take the unit square, and I'm gonna see what's gonna happen when I change the variables on that unit square. So I have this is x-axis, this is y-axis, and then I have the unit square. So this unit square in UV plane, it becomes what? I'm gonna take 0, 0, and let me actually write the change of variables that I have. U is 2x minus y, v is x minus 3y. So u is 2x minus y and v is x minus 3y. Okay, so when I have 0, 0, when I plug in 0, 0 in here, u and v would be 0, 0. Okay, so this is u and v. And now in the xy plane, in the uv plane, I have what? U and then v. So the origin goes to the origin. Okay, oops. What else? If I take this point in here, for example, the point 1 and 0, 1 and 0, then when x is 1, y is 0, u would be 2, and v, x is 1, y is 0 would be 1. This is u, v. Okay? So I get 1. Actually, let me make it a nice scale. 1, 2. So this is 2 and 1. 2 and 1. Therefore, this side in here becomes this side in here. Very good. So now let's take another point. For example, this point in here, the point 0 and 1. So the point 0 and 1 in xy plane becomes what? X would be 0, y is 1, so u would be negative 1. X would be 0, y is 1, so I get negative 3. This is my u and v. So negative 1, and then 1, 2, and then negative 3 would be somewhere in here. So this is negative 1 and negative 3. So this side in the xy plane becomes this side in here. Let's put the last point, which is the point 1, 1. So 1, 1 in the uv plane becomes what? X is 1, y is 1, so u is 1. X is 1, y is 1, u is negative 2. So this is the uv point. 1 and then negative 2. Very good. So these two sides becomes like this. Very good. So now what is the area of delta a prime? Delta a prime is what? Delta a prime would be the determinant of this matrix. Do you remember in the chapter that we talked about the cross product, the area of the parallelogram would be the length of one side cross product with the other side, if we consider it as a vector. So I get negative 1, negative 3 to 2 and 1. So it would be negative 1 plus 6, which would be 5. Okay, so the area here would be 5. The area of this one is just 1. So delta A in here, which was 1, is 5. Delta A prime is 5, and delta A is just 1. For any rectangle that we choose, the area after the transformation would be 5 times the area of that one. It's just because we have a nice linear transformation in here. So let me write that. For any other rectangles that we take, rectangles, the area is also multiple of 5. So in general, I can say delta A prime, the area after the transformation, would be 5 times delta A. So delta A prime, so dA prime would be 5 dA, and so du dv would be 5 times dx dy. And so inside the double integral, when I have dx dy, it would be 1 over 5. So you see dx dy would be 1 over 5 du dv. Very good. So that's how we transform x and y into u and v when we have this u and v. What's going on in general? So let's say we have u as a function of x and y, and we have v as a function of x and y. If you remember linear approximation, because u is a function of x and y, change in u would be partial derivative of u with respect to the first coordinate and then delta x plus u with respect to the second coordinate delta y. It is the same for dv. It would be v with respect to x delta v delta x plus partial derivative of v with respect to y delta y, which is basically, if I want to write this in the matrix notation, it would be delta u delta v, and it's approximately a matrix which is u with respect to x, u with respect to y, v with respect to x, v with respect to y, and then delta x delta y. Okay, so for a small rectangle in xy plane, it is going to be approximately a parallelogram in u and v. So small rectangle in xy plane is approximately a parallelogram. Let me move this one a little bit in UV plane. Okay, so let's see why. It's just because, you see, if I have this rectangle in here with delta x and delta y, I can say that this is delta x times I, this is delta y times j, and let's see what's gonna happen when I just basically move these vectors using this transformation. You see, I have like this. So delta x I would be what? Would be delta x and 0, right? So delta x 0, so the first coordinate, which would be, let me write this, the first coordinate, which is delta u, if I put delta x in here, if I put a 0 in here, it would be ux delta x. And then the second coordinate, which is dv, this is delta x, so this would be vx delta x, and then delta y would be 0, so it becomes that. So this is like this vector in here. This is that vector. And then, for example, delta yj is 0 delta y. Let's see, what is this vector using this transformation? So delta x is 0, so I'm gonna put 0 in here. So this part would be 0. Delta u would be just u with respect to y, delta y. And then delta x here would be 0, so I just get v with respect to y, delta y in here, right? So I have this vector, which would be something like that, okay? This vector in here. And then I get a parallelogram using this transformation, okay? So this is delta A. I'm gonna call the area of this parallelogram delta A prime, and so I see that the area of the parallelogram would be the determinant of this matrix that I have in here. And the matrix is u with respect to x, u with respect to y, v with respect to x, v with respect to y. Okay, just using the cross product of these two vectors, which are the sides of my parallelogram, I get this determinant times delta A. So I'm gonna define the This determinant, the determinant of this matrix, is called Jacobian. Okay, and on the next video we're gonna see how we can use Jacobian to transform to basically use it in the change of variables and change the double integral of delta x delta y to delta u delta v.